But you can look at it in the book and see that, this is what I've done. Like I said, this is a difference between the mean and the J treatment and the overall mean. And that's the difference between each data point and the mean in that treatment. But I was trying to get down to this equation so we could play with it just a little bit. And again, our objective is to understand how to partition it, which we've done. We've already partitioned it, right? We partitioned it into total variation, a treatment variation, and a random variation. So we've achieved that already. That's good. We've got the total, and you're going to see in the ANOVA table the letter T. We've got the treatment.
That is your goal.
You're going to see in the ANOVA table the TR when we look at it, and then we've got the error, and then that generic ANOVA table that's in the book, they're going to have E. So let's see, that generic ANOVA table is that one on page 23, yeah, table 2.2. So and so we've already achieved this piece of the objective, showing how to partition it. It was just a simple little bit of math. So now our next piece of objective is to show where this appears in the ANOVA table, and I should say where it appears and what it is mathematically. So we're not quite there, so we're going to be here. So I'll erase this, but I'll put this equation back up at the top. So we're going to play with it just a little bit. And again, I don't want you to really be thinking this is something you're going to have to calculate all the time. It's just so you can understand what's in the ANOVA table, and so you can explain it to people, at least use it properly. ANOVA is a tool that a lot of different disciplines use. The first person I ran into that used ANOVA was my colleague John Draper, who was a PhD psychologist I worked with out at the lab, and he was a factors guy. And the psychologists use ANOVA all the time. The clinical psychologists, the ones that do all the experiments. Right. I'll put all my bars on there. Yeah, so total treatment. Okay. So let's see. So what are we going to do? I'll tell you in words what we're going to do, and then I'll do some of it. Let's see. So what you do mathematically is you square the whole thing, just like you did in algebra. And why are we squaring it? Because remember, we're trying to get to an analysis of variance, and remember, variance has got a square in it. We've got an error term squared. So we're going to square the whole thing, like we do in algebra. Square that, square this. FOIL, remember the first order, the outer inner last thing, and then play algebra. Factor out things that out of sums that don't matter. Make terms that are 0 be 0, let's see, and come down to an answer that's going to be the values that appear in the ANOVA table. Let's see, I want to make a statement. That's good. Okay, and I think that's where we'll get to. Yeah, okay, so let me do that. And let's see, the math is ugly for two lines, and then it becomes ugly, and then it becomes words. So let's do it, and we'll see. Maybe you'll hate me, but it won't be only temporarily, right? So step one is square. Okay. All right, and I'll go back. I'll put the sums in. So let's see. Oh, square everything. Yeah, and then I forgot to tell you this too. Sum over I and j. So at least mathematically, I'm telling you what we're doing. So square it all. Square. Sum first over I. second of the J. Okay. And then we'll say, get out of the way. Square that. Remember algebra, this is an A, and this is a B, A squared plus 2AB plus B squared. After having a FOIL, so I'll write it in here. What's this? A squared. And I can keep the sum, I can put the sums in each one or keep it in, but I'll tell you what, I'll rewrite the sum every time, just so you see it. Some of the parentheses or some of the outside, doesn't matter. In fact, I'll keep it in the proper algebra order too, that may make it clearer to see. I'll make it easy so you can see it. Square thing. Sit here, let you guys catch up. Again, I'll make sure I didn't make any mistakes. So did you see I didn't do anything amazing? I squared this term and I'm just summing it up on the double sum. I squared this whole thing as a polynomial. Right? So I got that squared and I got that squared. And then I got the cross term, 2 of the product. Yeah, okay. So we're gonna reserve. Yeah, so we're kind of happy, just to give us thought here. We're kind of happy with this term, and kind of happy with this term, and kind of happy with this term. So let's be happy with them for just a minute, and let's focus in on this term, because there's some simplification we can do on that term that will basically make it go away, and so therefore. We'll be very happy. In fact, I could just sit here and say that. So look at it. In fact, why don't I do it that way? So what's going to happen is we're going to wind up in the end with this equals to that and that. This term that I circled here is going to be 0. Let me just show you that, and then we can know that we're down here at the end. In fact. Not anything incorrect. Yeah, no. So what will happen is, in the end, this is going to be SST. What does that mean? Sum of the square total. Okay. This is going to be SSTR. Sum of the square the treatment. Okay. And this is going to be SSE. Sum of the square the error part. And you'll see that in that ANOVA table, okay? Those letters, SST, SSTR, SSE. So in order to get that, and what it's saying is the total variation is a treatment error. In order to get that, we got to prove that what's in the circle is 0. Oh, okay, that's not bad. So step 1 was square everything and sum. We did that. And so step 2 is going to be make the circle 0. Okay, so now let's see. Step 2, the middle term with the cross term. Okay, all right, so remember that's the total, that's the treatment. 2.7, that's the error. Now, so now we're working on just that. So let's see. So first thing you'll notice is here, and I'll, right here, that one doesn't have any I indexes in it, does it? We've already summed over I here, we've already summed over I here. So this term has absolutely nothing to do with this I sum. It's as if it's a number just sitting in there. We can sum all this up, this is just factor out. Okay, that's good. Let's take that as step one. And why are we doing that? Because it's gonna, we'll see some things. So I'm just factoring that out since it had no I index. Well, you agree if I summed up a bunch of things, if I summed up a bunch of numbers, all of them multiplied by 2, or if I factored out the 2, summed up all the numbers, then multiplied by 2, the same thing, isn't it? So that's all I've got. Right, so nothing magic there. So, make sure I didn't make any mistakes. No, did not. Okay. And if we quit worrying about the 2 if we want to. We'll just quit worrying about that. We'll just look at that now. All right. Okay. That thing now, let's see. So that's our next step. Well, let's see. So now let's do algebra. So this is sum of j equals 1 to k. Here's I'm not going to do anything with that. I did make a mistake. I should come in. J. Each J, each one has a J on it. Yeah, so let's see. Seconds, because I don't think my thing is right. I don't want to get you wrong. Oh, okay, yeah. you add all these up, let's see, let me make sure I'm expressing it correctly. Right. Fix that. So I want to say. I think it's easier. Excuse me for sitting here like this. I don't think that's, they made a mistake. And they said that.
Look at that.
Yeah, they actually, I actually think they did. I think what they wanted to say was, all right.
Since it's a mean, you can just multiply by the
Yeah.
number of values.
That's what they're doing, yeah. Is that what you see they're doing? Yeah. But they took, you're saying this one here. Yeah, but they got it inside the parentheses. Right, see,
Right, so it's a,
they did this in the book. NJY dot, right? That's what the book says there. And you're right, they're just multiplying the mean by the number of values, but I don't think it should be inside the
I
sum.
think the sum should be, this should be the sum of the YIJ.
Like that.
Yeah.
Yeah, that's what I think. So that's why I was like, and my notes reflect what's in the book, and that's not right. And see, then, so that's what it should look like. And then this is the same thing then. But once you sum over that, this is NJY times the mean too. And so then therefore this whole thing equals 0. I don't want to dwell on it, but yeah, that's interesting. I'll check that and make sure, but I think that's a typo in the book. I think the parentheses should be moved like that. But you know it is, you can't just say y bar dot j is equal to nj y bar dot j, just a substitute. You see what I'm looking down at the bottom, page 20. So I'll check that, make sure that, yeah, that's not correct. So now, if that middle term becomes 0 because that's the correct math, then what you wound up with then, worked on that, that was 0. That was a great innovation. one of those where you put your nose, well, this is bad and wrong. So anyway, what we had left over was that double sum here, j equals 1 to k, I equals 1 to nj, of each data point minus the grand mean squared. We had sum over all the treatments, sum over all the samples of, and this is where, even if the one equation was goofy, we're happy with this one. Because this one kind of makes sense. Sum over all the treatments, over all the samples. So what do we come up with? Is that, hey, so let's make sure we got everything, we know what's going on. So this is the overall mean, or the grand mean here, the double dot one, and this is the group mean, if you will, the treatment under each treatment. It's the same thing here. Yeah. And this is the grand. And like we said a few minutes ago, so we've broken up the total variation. That is, the variation between each little data point and the whole mean, to two pieces. The difference between the group mean and the grand mean, and the difference between each data point and the group mean. So this is the treatment. This is the error. Okay. So now we're going to call this the sum of the square total, sum of the square treatment, sum of the square error. So let's see, sum of the square total equals sum of the square treatment plus sum of the square error. All right, so we've broken it up like that. Let's see. Now Excel, just so we know, this is what the book does. Excel does it this way. I think you'll see it's called SSA plus SSW, where A is among. This is within. You'll see other books make those words right. The treatment among the treatments, the error within a given treatment, that's the words. So yeah, I think that's Excel calls it that. So what, then the last thing you're going to have is that concept of degree of freedom. Remember, it was we saw that statistic before. Remember when you had a mean and you talked about summing up a bunch of numbers and how many of them could vary, and you had a series of numbers, 1, 2, 3, 4, 5, 6 equals some mean. You could vary 5 of them, but then the last one you couldn't if you had a fixed mean, and that was, so the degrees of freedom was always one less than the number of data points that you had, because the last one had to adhere to the mean equation. So let's look at what's in a typical. So when we play with ANOVA, so when you know the table, it's going to look like this. Let's go back to black so you can see it there. So it's going to have, this is for one factor. It's going to have SST, SS treatment, SS error. And then it's going to have okay, so this is the source. It's going to have the degrees of freedom. This will have BN minus 1. Sorry. In the table, it's going to be written backwards. Treatments, error, total. So this less degree of freedom than there are treatments. The total is n minus 1, and that man's got to sum up to that. So this is n minus k. Okay. Then you've got the sum of the square error. So you're going to have SSTR, SSE, SS total. And then you've got this mean square. All right. Okay. And what that is well, if we just added up all those sum of the squares, then the one with more of them is going to be bigger, right? In general, unless it's close. I mean, in general, if they're of the same magnitude, if I sum up 20 squares that have a difference of 1, and I sum up 5 that have a difference of 1, well, with 20 it's going to be bigger. So we've got to normalize it, right? So all this is this number divided by that number, this number divided by that number. So this is a normalized expression of the error to account for the number of terms in it. Since one of them may have a lot of terms in it, one of them may have fewer, we got to even the playing field, if you will. Okay, then we're going to have to make some decision. Well, hey, what decision is? It's going to be the F statistic, right? And it's going to be the ratio of the mean square of the treatment to the mean square of the error. That's our value that we're looking for. And then we're going to have a probability, and this is the probability that that you have an F statistic bigger than that. So remember, if it's very improbable that you had gotten an F statistic that big, then it's likely that the treatment is bigger than the error. And then XL also gives you the F critical out here too, in case you don't want to use probability, you want to compare it to an F critical. So yeah, so let's look at one. I guess we can finish for the day and revisit this for the next day and see why I did this in 2 pieces. So yeah, so here, let's see, here's example 2.1. So that's the, this example 2.1, is it the insulation or is it the, yeah, it's not the appraisal, it's the insulation. And so the first thing I did, I got you the notes on where the ANOVA is. And remember, you have to install it. It's under the add-ins, and then it's in the analysis on the data tab. Yeah, and that's how you get it in there. Okay, so let's see. So let's look at the example. You guys have done this enough, you know. So yeah, so it's the ceiling insulation. So the table's laid out like you want to. These are the treatments. These are the data points again. So you know, this would be the YIJs, right? This is Y33, all right? This is Y34. And then so N1 was 5, 4, 5, 3, 6. And let's see, the total number was 23. So there's all sorts of fun stuff like that. And let's see. Yeah, this is great. I don't have my tab.
On Blackboard?
What's that?
Is that on Blackboard?
Yeah, it is. Is it, did you, or on Canvas, whatever it is now? Yeah. Did you guys, were you able to get them? I think, Bill, you got them. I finally figured out you had to publish the module too. That doesn't show my tabs there. But yeah, it is on Blackboard. There we go, great. So, it's over here. So if you look under here, let's see. Not added in. I'm gonna bring mine over here. There. So there it is. So there's ANOVA under here. Single factor. You see there's others for 2 factors and stuff, but this is a single factor. You do that. Okay. So then what you do to do an ANOVA, you just select. I tend to like to select the labels too. Let's see. So you got to tell it. And then your output range, new worksheet, so we can say, okay, and there it comes. Yeah. And so, let's see, make sure I did it correctly, so it should look like, yeah.
You did that one more time?
Yeah, yeah. So you go under data, let's see, let's go, you're on your data page. Yeah. And so you're under data analysis and ANOVA single factor. Hey, lucky it's already selected this time because we are single factors, chapter 2. And select, you don't have to select the labels, but if you do, it makes that result table look a little better. So see, I selected everything. And then tell it you selected the labels if you did. And then you can put the output down here if you want to. I always put it on new worksheet. Then I can save it. See, there it is again. So if you didn't select those labels, these groups won't say 4, 6, 8, 10, 12. It'll say, in fact, I may not have done it over here. Let's see if I did. No, I did it over there too. It says something generic, group A, B, C, D, I think. I forget. Okay, so what you see is, just like I said, they're using between and within. So between, that's the treatment. Within, that's the error. Here's the total. So you will notice right away too that that plus that is that, right? Total had to add those two, just like we said. The degrees of freedom, there were 5 groups, so there's 4 degrees of freedom there. There were 23 total samples, so there's 22 degrees of freedom there. And then this is calculated as the difference between those two. So then this, the mean square error is the SS divided by that. This one is the SS within divided by its degrees of freedom. Okay, so then the F statistic is the ratio of that over that. And then the p-value, thinking about the F distribution, the critical value at 5%, and you know, why is it 5%? I didn't show that when I did the single factor ANOVA, there was a selection there for the percentage, what you wanted it to calculate for these two. Was it 5%, 10%? You put that in there. So at the 5% level, the critical value is 3. Well, we got an F of 36. So that's huge. You know, if we were thinking about the F distribution here, it looked like this. Peaks at 1. It says at 5% out here, and we'll talk about the F distribution next week. 2.92. That's for these 2 degrees of freedom. The F distribution changes depending on what these numbers are. There's a different number of F distributions, but for this particular one, the 5% F critical is this. Well, goodness, we had 36. You know, we're way out here. So the probability that you got that by just randomness is 0, right? 2 times 10 to the minus 8. So what that says statistically is, for this particular example, which was the insulation example, that the between group really was hugely larger than the within. In other words, the treatment had a huge difference compared to just random error. And so, wow, our conclusion is yes, the thickness of the insulation did have a significant impact on your energy bill. Well, you know, duh, but it's a good example, and it's nice. You know, you probably didn't need ANOVA perhaps to tell you that, but maybe you did. You'll just look at that, maybe. Yeah. You can see, right? I've used more energy, lesser. And generally, you can see how that, you know, it was. These are, I don't see any 14s or 15s over here. Lots of 12s, and I don't see any 12s over there. So I can do an ANOVA in my head and say, yeah, insulation did matter. And but rather than like you might have done in the olden days and just got a mean and said, yeah, the means are different. Well, we have done that in a sense, correct? We have done that in this table. We have gotten these means, and we have statistically calculated the variance amongst the means, and then statistically looked at the variance due to the treatment and that due to the error, and we've taken this nice ratio, and then we've made a statistical statement about it. So we're a lot stronger than just saying, oh, the means look different. Yeah, they do look different. How different do they look? Hugely different, and the probability of getting them that different with that type of random error was really small. Now, you're right, if we had another data set and we had more random error in it, then this would be bigger, right? And this F would be smaller, and you could see how if we had really sloppy, crappy experiments where we really poorly measured the kilowatt hours, then yeah, this could eventually, I mean, maybe not in this example, but in other examples where the data wasn't quite so biased, you can see how it could get to where, yeah, you could probably have just done that and the variation be just due to error. And so that's what you're seeing here. So let's see, in fact, there's another example, I'll pull it up and then we can talk about it next time, but the example 2.2 had the appraisers. It's right here. 2, yeah. Okay, so it had the house appraisers. And so this is a nice clean data set. We got 3 different appraisers, 5 samples each. Okay, so you look at those, bless you, and you're saying, is there a difference in these? You know, I don't know. Looking at them, I'd say no, perhaps. Oh, well, let's say no or yes with an ANOVA. So if you just do the same single factor ANOVA here, and yeah, I got the group names there. So let's see. So remember, this is between the appraisers. This is the error within the appraisers. There were what, 15 total data, 15 total appraisers, three appraisers, 5 houses each. So you can see that's 15 minus 1. There were 3 appraisers, that's 3 minus 1. That minus that is that. Here's our mean square errors. Here's our F, 2.3 at the 5% level with these degrees of freedom. Now you notice how that changed. The critical value at the 5% level was 3.9. That's less than 3.9. So that says, hey, we were over here. Now we were 3.9. We're over here at 2.3. Okay, so it says, oh, gee, there's a high probability that could have just been due to the randomness of those appraisers. And so the probability that you had a P that was that or bigger was 14%. No, you can't really statistically say there was a difference in the appraisers in that way. And so you can see, and we'll revisit this one again. And let's see, what did I do on this table just for fun? Yeah, I calculated those 2 numbers for you. That number are calculated over here if you wanted to make your own ANOVA table because you got excited. And you can see that when you're getting this probability, I've got the ratio, but also those 2 degrees of freedom in there. And you can see when I'm getting this critical value that I've got the 5%, 10% level, and the 2 degrees of freedom, so that's going to change. It's a function of the degrees of freedom, and we'll look at some F distributions next time. So at this point, you should be like, all right, what should you take away? You should take away that we've got this tool called ANOVA, and we'll explore it a little bit more next time. The tool does a statistical job of answering the question, what is the relative size of that compared to that? And when I say that compared to that, what is that? That's the sum of the square error there of the treatments, and this is the sum of the square error of the error, normalized, you know, but made the playing field equal by scaling it with the number of values in there. So we're statistically addressing the question, which was bigger, treatment error or random error, and we're doing it by comparing it to this F distribution. That's a nice distribution that changes based on how many items are part of it, but it's going to be just like the old T distribution we use, or the Z-score, those kind of things. It's going to come up with a probability. So all you need to know when you look at it, hey, wow, they're excited. So when you look at it, all you need to know is that 5% or less? If you're using the 5% level, is this bigger than that? To answer the question, yeah, the treatment mattered or it did not matter. In this case, it did not. And so we've got our tool, we know how to lay it out, and today we only covered the simplest thing, right? 1 factor, everybody was the equal playing field, all the samples could be randomly placed. So the rest of the class now, we'll keep going. We'll have different factors. We'll block them based on background variables. We'll do multiple ANOVAs because we may have 2 factors. We'll have interaction. We'll be able to account for all of these things. So you can see where we're going mathematically. We'll just further break this up and further have more statistics that we'll have to ask ourselves what level are they and they'll answer the questions that way. So, got us, I think. So we got the rest of this chapter next time, which should clear up some of this. So you should kind of be in a sort of a middle point now. Oh God, it's not, I kind of understand it, but I'm not yet. But hopefully you will, when we know what you have to do. And all of these, like I said, all these, if they're not on Canvas, let me know, and I'll just miss them.